Welcome to today's Explainer. We're jumping right into what I like to call the ultimate survival guide for developers, focusing entirely on exactly how JVM crashes get fixed. I mean, if you've ever dealt with an application just suddenly going down in production, you know the absolute panic and immense pressure that hits you, right? So today, we're taking our source material and translating it into a highly structured technical guide. We're going to look right under the hood at the precise mechanics of what happens when things go horribly wrong. But more importantly, we're exploring the exact methodologies and architectural adjustments you need to permanently fix these catastrophic system failures.
To actually conquer these high-stakes failures and get to that holy grail of perfect application stability, we have to realize something absolutely crucial. These issues are deeply interconnected. It's like a giant puzzle. You absolutely need a multi-pronged battle plan because, think about it, a silent memory exhaustion issue can easily trigger some really heavy garbage collection overhead. And what does that do? It generates massive latency, which then completely masks underlying class loader misconfigurations. It's a chain reaction. By treating all these zones as one continuous ecosystem, we stop just blindly guessing its symptoms. Instead, we can systematically diagnose and neutralize the actual root causes of our application instability. So here's our roadmap for today. 1. JVM crashes and fixes. 2. Solving out of memory. 3. Class loading and caching. 4. Observability and performance. And finally, 5. The Spring Framework lifecycle.
All right, let's jump straight into Section 1, JVM crashes and fixes. Why did the JVM just crash? Honestly, this is the single most urgent question a developer can face. But just asking it isn't enough. We need to know exactly where to look for the answers. Your very first step in diagnosing a fatal crash is hunting down that HS_error_PID fatal error log file generated by the JVM. Think of this file as your definitive black box. It gives us critical insight into native crashes, captures the exact thread states at the time of failure, and even flags problematic memory addresses. It literally gives us the raw data we absolutely need to start engineering a proper fix. Now, when that crash actually happens, the operating system throws us our first massive clue, a non-zero code exit. And these codes, they aren't just generic errors. They tell a very specific story about how the process died right at the OS level. For instance, if you see an exit code of 137, that immediately tells us, hey, the Linux out-of-memory killer just stepped in and forcefully terminated our process. On the flip side, a code of 143 means a standard SID term signal was sent. Understanding these specific codes is a real game changer because it directs our entire troubleshooting strategy right from minute one.
So to actually fix these crashes, we really have to dive deep into advanced memory investigation techniques. We do this by actively pulling heap dumps and analyzing them with memory profiling tools. What we're looking for specifically are those massive object retention trees that are just refusing to clear out. We also want to scrutinize the garbage collection logs for excessively long pause times, because those usually predicate an actual crash. By analyzing these complex resource patterns, we completely shift our approach. We go from just reacting to an outage to surgically fixing the underlying memory leak.
Moving right along to Section 2, solving out of memory.
Resolving an out-of-memory scenario takes real precision. It starts with identifying exactly which memory space has actually been exhausted. We really have to differentiate between a Java heap space error and a metaspace error, mostly because they require entirely different solutions. And look, implementing a fix isn't just about lazily cranking up that -XMX memory flag just to give the application more room to fail. That doesn't solve anything. Real debugging means optimizing heavy data structures, making absolutely sure I/O stream resources are properly closed, and hunting down those infinite loops so the memory exhaustion never, ever returns.
Let's shift gears a bit into Section 3, class loading and caching.
Understanding the JVM's hierarchical class loading structure, and by that I mean specifically the bootstrap, extension, and application loaders, actually provides the motive behind a lot of hidden application failures. This is especially true when you factor in really complex deployment environments or application servers like OSGI. In those environments, aggressive caching updates can inadvertently trap stale classes in memory. And when the class loader gets totally confused by these stale references sitting alongside your core runtime jars, well, that leads to some truly bizarre runtime crashes that are incredibly difficult to reproduce on your local machine.
Precision in identifying these class loader failures is absolutely critical. You really must understand the distinct technical difference between a class not found error and the similarly named class dev not found exception.
A class not found scenario usually happens when your code explicitly tries to load a class via reflection, like using class.forName, and it simply isn't in the class path. Conversely, that other exception, that means the class was successfully there during compile time, but it was completely missing or critically failed to initialize at runtime. That points to a much deeper deployment issue.
All right, Section 4, Observability and Performance.
The great thing is, we can act proactively against these failures by heavily tracking latency and executing what we call latency purges. High latency is very often a direct symptom of underlying issues. Think excessive garbage collection overhead that's just struggling to free up space. Executing a latency purge means you are proactively profiling thread contention across your application. You're optimizing overloaded database connection pools, or maybe even tweaking your JVM by switching to more efficient GC algorithms like G1GC or ZGC. Doing all this purges the degradation long before it can cascade into a fatal crash.
And finally, Section 5, Spring Framework Lifecycle.
System stability is directly, inextricably linked to how well we architect our Spring component diagrams and manage overarching lifecycle methods. Poor component architecture directly impacts the JVM. For example, if you create complex circular dependencies or load up unnecessarily heavy singleton beans, that can silently bloat the JVM heap right at startup. This total lack of lifecycle management can cause fatal out-of-memory errors and literally crash your application before it has the chance to serve even a single user request. No way you want that.
Mastering this three-step lifecycle flow is exactly how you fundamentally prevent those startup crashes. It starts with basic bean initialization, moves smoothly into the auto-wire phase for dependency injection, and, crucially, wraps up with post-construct execution. The huge technical takeaway right here is that heavy I/O operations or extensive database calls should never, ever be placed in the raw initialization phase. They absolutely must be safely handled via @post-construct annotations or application events. That guarantees your context loads cleanly and safely every single time.
So, as we wrap up this explainer, I want to leave you with this crucial thought to take back to your own codebase. Are your architectural foundations actually clean, or are you just waiting for the next non-zero code to strike? Fixing JVM crashes isn't just about reacting to terminal logs after the damage is already done. It is about deliberately engineering resilience from the ground up, starting with your very first line of configuration. Thank you so much for joining me today. Take these architectural frameworks, apply them to your deployments, and I'll catch you in the next one.